Habitable planets beyond Earth are not just theories anymore. Scientists are now discovering worlds that may offer better conditions for life than the place we call home. These discoveries are forcing us to rethink what it means for a planet to be perfect for life. Earth has been our reference point for billions of years, but as we look deeper into space, we are starting to see something surprising. The universe may hold planets that are more stable, more protected, more fertile, and more supportive of life than Earth has ever been. This idea sounds almost impossible, but the evidence continues to grow every year. The search for superhabitable planets has officially begun. The idea of planets more habitable than Earth began as a theoretical concept. For a long time, scientists assumed that Earth represented the ideal conditions for life because we know life thrives here. But when researchers started studying how planets form and evolve, they realized Earth might not actually be the most optimized environment. Earth has ice ages, unstable climate cycles, large deserts, and regions with limited life. It has endured mass extinctions that nearly wiped everything out multiple times. It has changing magnetic fields, drifting continents, and a future where the sun will eventually heat up enough to make Earth uninhabitable. These limitations made scientists wonder if better worlds could exist. The term superhabitable planets was introduced to describe worlds that could be more suitable for life than Earth. To be superhabitable, a planet must have features that enhance stability, biodiversity, and long-term habitability. These features include mild temperatures, shallow oceans, a stable atmosphere, a strong magnetic field, and a star that remains calm for billions of years. A superhabitable planet might also be slightly larger than Earth, providing more surface area and potentially more ecosystems. It might orbit a star that is smaller and longer lived than our Sun, giving life more time to evolve. Many of these traits exist in known exoplanets, making the idea of superhabitable worlds increasingly realistic. For most of human history, we had no idea what existed beyond our solar system. The night sky looked like a collection of stars with no planets. But that illusion ended in 1992, when scientists discovered the first confirmed exoplanets. Since then, more than 5,000 exoplanets have been identified, with thousands more awaiting confirmation. As we examined these new worlds, we found massive gas giants, frozen planets, rocky worlds, lava planets, water planets, and planets with atmospheric signatures unlike anything in our system. With each discovery, we learned that planets come in endless varieties, and some of them show real potential for habitability. The key conditions for habitability are liquid water, a stable temperature, and the right kind of atmosphere. Earth sits in the Sun's habitable zone, where temperatures allow liquid water on the surface, but Earth is on the inner edge of this zone, meaning it receives a bit more heat than ideal. Some superhabitable planets might sit closer to the middle of their star's habitable zone, giving them more stable temperatures over long periods. Stability is essential for life because dramatic temperature shifts can disrupt ecosystems, cause mass extinctions, or prevent complex organisms from evolving. Another important factor is the type of star a planet orbits. Our Sun is a G-type star, which shines brightly but has a shorter lifespan compared to other types of stars. After about 10 billion years, the Sun will expand and destroy Earth. In contrast, K-type stars are cooler, more stable, and can live for tens of billions of years. These stars offer more time for life to develop. Many potentially superhabitable planets orbit K-type stars. They may be older than Earth, giving life a head start of billions of years. A world orbiting such a star might host ecosystems far more mature and complex than anything on Earth. Planet size also plays a major role in habitability. A planet slightly larger than Earth, about 1.2 to 1.5 times Earth's radius, could be ideal. This size gives the planet stronger gravity, which helps maintain a thicker atmosphere. A thicker atmosphere provides better protection from radiation, stabilizes temperature, and supports higher oxygen levels. But if a planet is too large, it can become a gas giant or super-Earth with crushing surface conditions. The sweet spot lies in a narrow range where the planet is big enough to hold a stable atmosphere, but small enough to remain rocky. Many super-habitable candidates appear to have shallow oceans, which may be better for biodiversity than Earth's deep oceans. Deep oceans can trap nutrients and create isolated environments. Shallow oceans allow sunlight to penetrate more effectively, supporting more photosynthetic life. They also create more coastal regions, which tend to be rich in biological activity. A super-habitable planet with large shallow seas and long coastlines could support more species than Earth ever has. Temperature consistency is another key factor. Earth's climate fluctuates due to its tilt, orbit, and geological activity, but some exoplanets may have more stable climates due to slower rotation, more circular orbits, or stronger atmospheric circulation. A world with minimal temperature swings would allow life to flourish without repeated cycles of destruction. Stability enables ecosystems to evolve over long stretches of time without interruption. Geological activity also influences habitability. Earth's plate tectonics help regulate carbon dioxide by recycling it through the crust. This system acts as a natural climate regulator. Without plate tectonics, a planet can become too hot or too cold. Some exoplanets may have more active tectonics than Earth, providing even better long-term climate control. Others may be more stable, internally reducing catastrophic volcanic events that disrupt life. Magnetic fields are just as important. Earth's magnetic field protects us from solar radiation. Without it, the atmosphere would slowly erode, and life would struggle to survive on the surface. Some super-habitable planets may have stronger magnetic fields due to their size and rotation. These fields would provide exceptional protection, creating a more secure environment for life to evolve. The search for super-habitable planets often focuses on systems with multiple potentially habitable worlds. Some planetary systems contain several Earth-sized planets within their star's habitable zone. These systems might host multiple super-habitable planets at once. If life developed on several of these worlds, they could exchange microbes through meteor impacts, a process known as panspermia. This would accelerate biological evolution and create diverse ecosystems. One of the most interesting superhabitable candidates is Kepler 442b. This planet lies in its star's habitable zone and is slightly larger than Earth. It receives just the right amount of energy and likely has a stable environment. Another candidate is Kepler 22b, which may have a water-rich surface. LHS 1140b is another promising world with a dense atmosphere and rocky surface. These planets are among hundreds that could support life, but some planets go beyond habitability. They might be better than Earth. For example, worlds with more mild climates, richer ecosystems, and more stable conditions could host life that thrives more easily. Life might even be more diverse or more resilient than life on Earth. If such a planet exists, it might look like a lush, vibrant world with forests, shallow seas, abundant water, and conditions that support a wide variety of species. The discovery of superhabitable planets also raises philosophical questions. If planets better than Earth exist, then life may be common in the universe. Intelligent life may evolve more readily in stable environments. Civilizations could arise on planets with long-lasting climates and abundant resources. These civilizations might be older and more advanced than humanity. The existence of superhabitable worlds suggests that Earth may not be the best example of a life-bearing planet. It is simply the one we know. These possibilities push scientists to develop better detection tools. Telescopes, like the James Webb Space Telescope, are beginning to study the atmospheres of distant planets. By analysing light passing through an exoplanet's atmosphere, scientists can detect molecules like oxygen, methane, and water vapour. These biosignatures could reveal the presence of life. Future telescopes will be even more powerful, allowing us to detect continents, clouds, and seasonal changes on distant worlds. The search for better-than-Earth planets is not just about curiosity. It may one day guide humanity's future. If we discover a world more stable, more fertile, and more protective than Earth, it could become a target for exploration or even distant future colonization. A superhabitable world might offer a backup for humanity or a new home for future generations. But even if we never reach these planets physically, knowing they exist changes our understanding of life's place in the universe. Right now, the idea of planets more habitable than Earth is one of the most exciting frontiers in astronomy. Scientists continue to discover new candidates every year. As our tools improve, our picture of the universe becomes clearer. Earth remains our home and the origin of life as we know it. But the universe may contain billions of worlds that surpass it in beauty, stability, and potential. And this journey is just beginning. Superhabitable worlds are becoming one of the most fascinating ideas in modern astronomy because they challenge the belief that Earth represents the perfect balance for life. When scientists began comparing Earth to potential exoplanets, they realized that many of the factors we assumed were ideal are actually compromises. Earth is habitable, but not optimal. It supports life, but not as efficiently or as safely as other planets might. Understanding what makes a planet superhabitable helps us see why the universe may be filled with worlds even better suited for life than our own. One of the most important qualities of a superhabitable planet is temperature stability. Earth's climate has changed drastically over its history. Ice ages, mass extinctions, rapid heating events, and atmospheric shifts have repeatedly reshaped life on our planet. These fluctuations show how fragile Earth's conditions can be. A superhabitable planet would likely avoid extreme climate swings. It would have a more circular orbit, reducing seasonal variations. It would rotate it at a rate that distributes heat evenly across its surface. And it would orbit a stable star, one that does not flare violently or brighten unpredictably. A stable climate allows life to flourish over long periods without constant interruptions. A planet's position in the habitable zone also matters. Earth sits near the inner edge of the Sun's habitable zone, meaning it receives more heat than ideal. If Earth were only slightly closer to the Sun, it would become uninhabitable. A superhabitable world would be located in the centre of its star's habitable zone, where temperatures stay consistently mild. This central position gives life more time to evolve and reduces the risk of runaway greenhouse effects or freezing events. The type of star a planet orbits plays a major role in its long-term habitability. Our Sun is bright and powerful, but it has a limited lifetime. It will run out of fuel in a few billion years, expand into a red giant, and destroy Earth. K-type stars, however, live far longer, up to 30 or even 40 billion years. They burn more slowly, remain stable for longer periods, and produce fewer harmful ultraviolets. Many superhabitable planets are expected to orbit these stars. A long-lived star gives life billions of extra years to develop complexity. On Earth, complex life took more than 3 billion years to appear. A planet orbiting a K-type star could have an immense evolutionary advantage, simply because it has more time. The size of a superhabitable planet is also crucial. Earth's size works well, but a slightly larger world, around 10 to 20% bigger, could offer more advantages. A bigger planet has stronger gravity, which helps maintain a thicker atmosphere. That thicker atmosphere protects life from cosmic radiation and stabilizes temperature. It also improves oxygen retention, which can create a more breathable environment if life evolves in that direction. A thicker atmosphere also makes weather patterns gentler and more predictable. On a superhabitable world, storms might be milder, temperatures more consistent, and climate zones more balanced. Land-to-water ratio is another overlooked factor. Earth's oceans are deep, and most of the planet is covered by water. While this supports life, it limits coastal regions, which tend to be the most biologically productive environments. On a superhabitable planet, oceans might be shallower, creating more continental shelves. These regions are rich in nutrients and support abundant biodiversity. A world with more shallow seas and wider coastlines could host ecosystems far more diverse than Earth's. A planet's surface temperature also influences habitability. Earth's average temperature is suitable for life, but much of the planet is too cold or too hot for most species. A superhabitable world would have more of its surface within a mild, comfortable temperature range. It might have fewer deserts, fewer frozen regions, and more temperate climates. This wider band of habitability would allow species to spread more easily and ecosystems to become more complex. Plate tectonics also play a role in long-term habitability. Earth's plate tectonics help regulate CO2 levels, balancing the greenhouse effect. Without this system, Earth might have become too hot or too cold. A superhabitable world would likely have gentle, long-lasting tectonic activity that maintains climate stability without causing excessive volcanic disasters. Smooth geological processes help maintain nutrient cycles, ocean chemistry, and atmospheric composition. Magnetic fields are equally essential. Earth's magnetic field protects us from solar wind and cosmic radiation. Without it, the atmosphere would slowly erode and the surface would be bombarded with harmful particles. A slightly larger planet with a molten iron core might have a stronger magnetic field than Earth, providing even better protection. This shield would allow life to flourish on the surface, rather than being forced underground or underwater. Atmosphere composition is another factor that shapes habitability. A superhabitable world might have a slightly higher oxygen concentration than Earth, supporting larger animals or more energy-efficient metabolism. However, too much oxygen would be dangerous, so the balance must be right. The planet's atmosphere must also regulate greenhouse gases effectively to prevent runaway heating or freezing. A thicker, well-balanced atmosphere can create a stable environment for billions of years. One of the most intriguing qualities of superhabitable planets is the potential for richer biodiversity. If a world has more stable temperatures, more shallow seas, more coastal regions, and more uniform climates, then life could spread more rapidly and diversify more easily. Evolutionary pressure would be high, but catastrophic events would be rare. Life would have long periods of uninterrupted stability, allowing ecosystems to expand and develop complexity. On Earth, biodiversity grows during calm periods and collapses during catastrophic ones. A world with fewer collapses would continuously accumulate new forms of life. The age of the planet also matters. Earth is about 4.5 billion years old, and complex life emerged only in the last 500 million years. If a superhabitable planet is 6, 7, or even 8 billion years old, life there might be far more advanced. Evolution would have had more time to explore biological possibilities. Intelligent life could emerge more easily. A superhabitable planet older than Earth could host civilizations far ahead of our own. Another unusual factor involves planetary rotation. A planet that rotates slightly slower than Earth might have longer days, reducing temperature extremes between day and night. But if it rotates too slowly, one side may become too hot while the other freezes. The perfect balance would create a stable global climate. Some planets may even be tidally locked, but still habitable if their atmospheres redistribute heat efficiently. These twilight zone worlds could have permanent regions of mild temperatures. A superhabitable planet might also benefit from having multiple small moons. Earth's moon stabilizes our axial tilt, preventing extreme climate swings. A planet with more than one moon could experience even greater stability. This balance reduces destructive weather patterns and climate cycles, making the world more predictable for life. Chemical composition is another important trait. A superhabitable world might have richer soils, more minerals suited for biology, and oceans with ideal nutrient balances. It might lack toxic elements that complicate life on Earth. Its chemistry could support unique forms of life, with higher resilience or faster growth rates. Even the colour of the star matters. K-type stars emit softer, more golden light compared to our Sun. Life might adapt to this light more efficiently, allowing plants or plant-like organisms to use a wider range of wavelengths. Photosynthesis could be more efficient, supporting richer food webs. In this sense, a superhabitable world could be greener, lusher, and biologically denser than Earth. All these qualities, stable climate, shallow oceans, strong magnetic fields, gentle tectonics, rich chemistry, optimal star type, and long lifespan, combine to create worlds that could support life far more easily than Earth ever has. Earth remains incredible, but it is limited by cycles, crises, and geological instability. A superhabitable world would be smoother, steadier, and longer lasting. As scientists search for such planets, they use data from telescopes to analyze atmospheres, orbits, temperatures, and star types. Every new candidate brings us closer to understanding habitability on a cosmic scale. And the more we study, the more we realize that Earth is not the peak of habitability. It is just one example among countless possibilities. Planets that may be more habitable than Earth are no longer hypothetical. Scientists have already identified several real exoplanets that fit many of the traits of superhabitable worlds. These planets are not science fiction. They orbit real stars. They have real measurements, real atmospheres, and real potential. And although we cannot visit them, the data we have is enough to suggest that some might offer better environments for life than Earth ever has. These planets are scattered across our galaxy, each with unique strengths that make them exciting candidates for superhabitability. One of the most promising worlds is Kepler 442b. This exoplanet orbits a stable K-type star about 1,200 light-years away. It is slightly larger than Earth, but not so large that it becomes a gas world. Kepler 442b receives just enough energy from its star to maintain liquid water, and its orbit sits near the centre of the habitable zone. Being in this ideal location gives it consistent temperatures that are more stable than what Earth experiences. Scientists believe this stability alone makes Kepler 442b one of the strongest superhabitable candidates we know. It also orbits a star that will remain stable far longer than the Sun, giving life more time to evolve. If conditions on the surface are mild and the atmosphere is thick enough, this world could support forests, oceans, and ecosystems richer and calmer than those on Earth. Another interesting world is Kepler 22b. This planet lies about 600 light-years away and orbits a Sun-like star, but it receives slightly less heat than Earth does. Kepler 22b could be covered in oceans, possibly forming a water world. If the oceans are shallow, the planet could be incredibly rich in life. If the oceans are deep, life may still exist but remain isolated. Kepler 22b is larger than Earth, which suggests it may have a stable atmosphere, capable of regulating heat more effectively. The balance of temperature and its orbit position make this planet a strong candidate for habitability. Scientists believe that if Kepler 22b has a rocky surface with shallow seas, it could outperform Earth in terms of biological productivity. LHS 1140b is another promising superhabitable candidate. It orbits a small stable red dwarf star about 40 light-years away, making it one of the closer candidates. LHS 1140b is a dense rocky planet that likely has a thick atmosphere. Unlike many planets around red dwarfs, it appears to have avoided destructive stellar flares. This gives it a strong chance of maintaining habitability. Early models also suggest that LHS 1140b may contain large oceans. If this is true, the combination of oceans, dense atmosphere, and stable rotation could create an environment where life thrives. A planet like this might remain habitable for billions of years, longer than Earth's remaining lifespan. Another superhabitable candidate is K2-18b. This planet is larger than Earth and orbits in the habitable zone of a cool star about 120 light-years away. What makes K2-18b special is the detection of water vapour in its atmosphere. This discovery raised the possibility of clouds, rain, and a stable water cycle. Some models suggest that K2-18b may be a Hycean world, a planet with a hydrogen-rich atmosphere and warm oceans. If so, it could support life in ways very different from Earth. Hycean planets might host microbial life in warm, nutrient-rich waters beneath thick atmospheres. Some could be even more stable than Earth, because their atmospheres regulate temperature extremely efficiently. K2-18b may not resemble Earth visually, but it could be more biologically productive. Kepler 452b, often called Earth's cousin, is another exciting candidate. It is about 60% larger than Earth and orbits a star similar to the Sun. Its position in the habitable zone suggests moderate temperatures. Because the planet is older than Earth, life on Kepler 452b could have had a significant head start. With billions of extra years, ecosystems could have reached a complexity we cannot imagine. However, if the planet is too large, it might have a thicker crust and reduced tectonic activity. Without tectonics, climate regulation becomes more difficult. Scientists still consider it a strong candidate, but one with uncertainties. One of the most fascinating systems for potential habitability is the TRAPPIST-1 system. It contains 7 Earth-sized planets orbiting a cool, dim star. 3 of these planets lie in the habitable zone. TRAPPIST-1d, TRAPPIST-1e, and TRAPPIST-1f are especially intriguing. TRAPPIST-1e stands out because it is nearly identical to Earth in size and density. It receives almost the same amount of energy from its star as Earth does from the Sun. Its temperature is likely mild, and its atmosphere may be thick enough to maintain liquid water. Because the star is extremely stable and long-lived, TRAPPIST-1e could remain habitable for tens of billions of years. Life there could evolve under stable conditions for longer than life on Earth ever will. TRAPPIST-1f and TRAPPIST-1d may also be habitable, but TRAPPIST-1e remains the strongest candidate. Another remarkable candidate is Teegarden star B. This planet is very close, only 12 light-years away, and it is one of the most Earth-like planets ever found in terms of temperature and orbit. It receives a similar amount of energy as Earth, sits comfortably in the habitable zone, and orbits a calm star. Early studies suggest it has a high probability of possessing liquid water. Because it is so close to Earth, future telescopes may be able to study its atmosphere in detail. If Teegarden star B turns out to be rocky with a stable atmosphere, it could easily qualify as a super-habitable world. Then there is Tau Ceti E and F, which orbit a Sun-like star only 12 light-years away. These planets are larger than Earth and potentially rocky. Their star has a lower luminosity, meaning their habitable zone is closer in. Tau Ceti A may be too hot, but Tau Ceti F sits in a position that could be ideal for habitability. If it has a thick atmosphere to regulate heat, it might host conditions better than Earth. Tau Ceti is an old star with high stability, meaning life on its planets could have had billions of extra years to evolve. Another fascinating world is Kepler-62f. This planet lies in the habitable zone of a dim K-type star and is believed to be a water-rich super-Earth. If it has an atmosphere similar to Earth's, it could be among the best candidates for habitability. Its orbit is nearly circular, giving it consistent temperature. Its star is stable and long-lived. The balance of these factors makes Kepler-62f incredibly interesting. Many of these planets share traits Earth lacks. They orbit stable stars, have thicker atmospheres, maintain more consistent temperatures, or offer larger habitable surfaces. Some could be covered in shallow oceans, others could be lush with vegetation-like life. Some could host ecosystems far older and more complex than anything Earth has seen. Scientists use several methods to identify these planets. The transit method measures dips in starlight when a planet passes in front of its star. The radial velocity method detects tiny wobbles in a star's motion, caused by an orbiting planet. Future telescopes will use direct imaging to photograph exoplanets and study their atmospheres. With each improvement in technology, our list of promising worlds grows. Some planets remain mysterious because their atmospheres are unknown. A planet may appear super-habitable from its orbit and size, but without atmospheric data, final confirmation is impossible. However, the discovery of so many promising worlds suggests that super-habitability might be common in our galaxy. The idea that Earth is not special can be uncomfortable, but it is also inspiring. If planets better suited for life exist, then the universe may be filled with thriving ecosystems. Intelligent life might be more common than we think. Civilizations might evolve under more stable conditions, giving them time to grow without the interruptions Earth has faced. As telescopes improve, we are entering an era where we can analyze the atmospheres of distant worlds for gases like oxygen, methane, and carbon dioxide. These gases could reveal biological activity. A world with better conditions than Earth could show stronger biosignatures. It could glow with chemical signatures that point directly to toward life. The search for super-habitable worlds is not just about science, it is also about imagination. It challenges us to picture forests under alien skies, oceans with unfamiliar life, continents shaped by different geology, and atmospheres with gentle winds and stable climates. These worlds could exist right now, orbiting quietly around distant stars. Earth is the only world we know with life, but that does not mean it is the best possible place for life. When scientists began to seriously study habitability, they looked at Earth not as the perfect template, but as one example among many. And as they compared Earth's properties to the traits of potentially super-habitable planets, they realized something surprising. Earth has limitations, weaknesses, and imperfections that make it far from ideal. Life flourishes here because it adapted to Earth, not because Earth is perfectly suited for life. If life had evolved elsewhere under better conditions, that planet might look even more vibrant and stable than our own. Understanding Earth's shortcomings helps us imagine just how much more welcoming some planets might be. The first major issue is Earth's unstable climate. Over the past billions of years, Earth has gone through extreme transformations. It has been a frozen snowball from pole to pole. It has suffocated under high carbon dioxide. It has roasted through intense heat spikes. Entire oceans may have boiled away during early phases. Climate change is not new to Earth. It has been happening since the beginning. These dramatic climate swings disrupted life repeatedly, causing bottlenecks and mass extinctions. A planet with more stable conditions would allow life to evolve continuously without so many global resets. Earth's history is filled with near catastrophes. A more stable world would not expose its ecosystems to such violence. Another limitation is Earth's position in the habitable zone. Earth sits close to the inner edge of the zone, meaning it receives more sunlight and heat than a perfectly mild planet would. Small increases in solar brightness could push Earth into a runaway greenhouse effect. Over long timescales, this makes Earth's future fragile. A planet positioned in the centre of its habitable zone has a much larger safety margin. It could tolerate fluctuations in atmospheric composition or changes in stellar output without becoming uninhabitable. Earth's position worked for billions of years, but it is not ideal for long-term stability. Earth's star, the Sun, also presents challenges. The Sun is relatively stable today, but its early years were violent. It emitted strong solar winds and intense ultraviolet radiation that could have stripped Earth's atmosphere if not for our magnetic field. In the future, the Sun will become more luminous, slowly heating Earth until it can no longer sustain life. The Sun's lifespan is about 10 billion years, but that includes billions of years when conditions were hostile or will become hostile. Some stars offer far better conditions for life. K-type stars, for example, are smaller, calmer, and live 3 to 4 times longer than the Sun. They give planets more time to evolve complex life and maintain stability. A planet orbiting such a star would have a long-lasting window of habitability, something Earth lacks. Another issue is Earth's atmosphere. While it is breathable and protective, it is also thin compared to what could be ideal. A thicker atmosphere provides better climate regulation and shields the surface from cosmic radiation. Earth's magnetic field protects us, but it has weakened and reversed many times. During these reversals, the planet becomes more vulnerable to solar radiation. A slightly larger super-Earth with a stronger core could produce a magnetic field far more stable than Earth's. offering stronger atmospheric protection. Earth's atmosphere is good, but not the best possible. The distribution of land and water on Earth also limits its potential. Earth's oceans are deep, covering more than 70% of the surface. Deep oceans trap nutrients at the bottom, limiting their availability for surface ecosystems. Large deserts, frozen poles, and mountainous regions also reduce Earth's habitable surface area. On a superhabitable planet, oceans might be shallower, allowing more sunlight to penetrate and more nutrients to circulate. This would create richer coastal zones and support more diverse marine life. A world with more evenly distributed land and shallow seas could offer far more habitable territory than Earth. Earth's geological activity is another double-edged sword. Plate tectonics help regulate climate by recycling carbon, but they also create destructive earthquakes and volcanic supereruptions that can devastate life. A superhabitable planet might have gentler, more regular tectonics that maintain climate stability without causing massive destruction. Earth also has hotspots beneath the crust that trigger volcanic activity. Large volcanic events can change climate globally for years. A planet with smoother geological processes would avoid these disruptions. Earth has experienced at least 5 major mass extinctions, each wiping out large portions of life. These events were caused by asteroid impacts, volcanic eruptions, climate shifts, and other catastrophic forces. While Earth recovered each time, these setbacks delayed the development of complex life by millions of years. On a more stable planet with fewer disasters, life could continue evolving uninterrupted. It might reach complexity earlier and achieve greater biodiversity. Earth's violent history shows clearly that habitability is fragile. A superhabitable world would avoid or minimize these destructive cycles. Another problem is Earth's tilt. Earth is tilted at about 23.5 degrees, creating seasons. While seasons can benefit some ecosystems, extreme tilts cause severe seasonal temperature swings. Earth's tilt also changes slowly over tens of thousands of years, affecting climate patterns in cycles known as Milankovitch cycles. These cycles have triggered ice ages and warming periods. A planet with a more stable tilt, or with multiple moons to regulate it, would avoid such dramatic swings. Stability is one of the most important traits for long-term life, and Earth's tilt is not as stable as it could be. Earth's rotation speed also creates limitations. Our 24-hour day-night cycle shapes temperature patterns, but planets with slightly slower rotation could experience smoother temperature transitions between day and night. A too slow rotation becomes dangerous, but a moderately slower rotation may provide an ideal thermal balance. Some superhabitable planets may rotate just slowly enough to reduce climate variability without causing extreme heating or cooling. Earth's rotation is not optimized for stability. It is simply what our planet ended up with. The distribution of continents also affects habitability. Earth's continents drift across the surface, forming and breaking apart in cycles. These rearrangements alter ocean currents, atmospheric circulation, and climate. While tectonic movement is necessary, Earth's cycles often cause massive environmental disruptions. A planet with more stable supercontinents or steady land distribution could maintain long-term climate patterns more effectively. Earth's geology is dynamic, sometimes too dynamic for consistent habitability. Another limitation is Earth's age relative to life's development. Complex life took more than 3 billion years to emerge. life on Earth was microbial for most of its history. A super-habitable planet older than Earth by 1 billion or 2 years might already host advanced ecosystems, complex organisms, or even civilizations. Earth's relatively late emergence of complexity is not a universal rule. Other planets may achieve this much sooner or under better conditions. Even Earth's oxygen levels have fluctuated dramatically. For long periods, oxygen was low, limiting complex life. Today's oxygen level of about 21% is suitable, but slightly higher oxygen could support larger, more energy-demanding organisms. Too much oxygen becomes dangerous, but planets with mild, balanced, oxygen-rich atmospheres could push life into forms Earth never could support. Earth's oxygenation history shows how unpredictable and uneven its habitability truly is. Radiation levels on Earth also pose challenges. Cosmic rays, solar storms, and background radiation affect DNA. While life adapted, higher radiation levels slow the development of complex organisms. A superhabitable planet with a thicker atmosphere, stronger magnetic field, and calmer star could expose life to far less radiation. Mutations would still occur, but not at rates that threaten long-term stability. Asteroid impacts are another major threat. Earth lives in a relatively crowded region of the solar system. The asteroid belt, near-Earth objects, and long-period comets all pose risks. A planet in a more isolated region, or within a system with fewer debris fields, would be far safer. Earth's history includes several catastrophic impacts that nearly extinguished life. A safer cosmic environment would allow life to progress uninterrupted for billions of years. Even Earth's biodiversity patterns reveal limitations. Earth's ecosystems depend heavily on climate zones, which shift constantly. Large deserts limit biological richness. Polar regions remain mostly barren. If Earth's temperature range were narrower, more of the planet could host life. On a superhabitable world, more of the surface might be covered in temperate forests, warm oceans, marshlands, coral environments, and fertile plains. The potential for biodiversity could be far greater. Finally, Earth's future is limited. In about 1 billion years, the sun will grow hotter, warming Earth enough to evaporate oceans. The planet will become uninhabitable long before the sun becomes a red giant. A superhabitable world orbiting a long-lived star could remain stable for tens of billions of years. Life could evolve for far longer than Earth ever allows. When we look at Earth's shortcomings, unstable climate, violent history, unpredictable geology, uneven temperature, limited biodiversity zones, moderate radiation protection, and a star that is aging quickly, it becomes clear that Earth is not the perfect blueprint for habitability. Life thrives here because it adapted to these conditions, not because these conditions are ideal. Superhabitable worlds represent the possibility that nature can build better versions of habitable planets. Worlds with more stable climates, more protective atmospheres, more balanced land and oceans, longer-lived stars, and gentler geological cycles might support life more successfully than Earth. These worlds could be far more common than we once thought. Finding planets more habitable than Earth is one of the most challenging scientific pursuits ever attempted. These planets orbit stars so far away that their light takes years, centuries, or even millennia to reach us. They are too distant to visit, too dim to observe directly with ordinary telescopes, and too small to stand out against the brightness of their stars. Yet, despite these challenges, scientists have developed powerful methods for detecting these distant worlds and analysing their conditions. The search for super-habitable planets depends on a combination of precision instruments, clever techniques, and deep understanding of how planets affect their stars. Each new discovery brings us closer to finding worlds that surpass Earth in stability, richness, and biological potential. The most widely used method for discovering exoplanets is the transit method. This technique measures tiny dips in a star's brightness when a planet passes in front of it. Even a small planet blocks a tiny fraction of starlight. When this happens at predictable intervals, scientists can confirm that a planet is orbiting the star. The transit method has been responsible for discovering thousands of exoplanets. Telescopes like Kepler, TESS, and the upcoming Plato mission use this method to scan large areas of the sky. By analysing transit patterns, scientists can determine a planet's size, orbit, and position within the habitable zone. For super-habitable candidates, this method helps identify planets slightly larger than Earth that orbit within the optimal distance from their star. Another important method is radial velocity. This technique measures the wobble of a star caused by the gravitational pull of an orbiting planet. When a planet orbits, the star shifts slightly toward and away from us. Sensitive instruments detect these tiny movements through changes in the star's spectral lines. Radial velocity helps scientists determine the planet's mass, which is crucial for identifying super-Earths and potentially super-habitable worlds. This method is especially useful for nearby stars and planets that may not transit from our viewpoint. Radial velocity complements the transit method by providing mass data that helps confirm whether a planet is rocky or gaseous. Direct imaging is another method. Though far more difficult, stars are so bright that their light overwhelms the faint glow of orbiting planets. Specialized instruments use coronagraphs or star shades to block starlight and reveal the tiny dots of light that are planets. Direct imaging is currently limited to large planets far from their stars, but future telescopes may be able to image Earth-like planets directly. When that happens, scientists will be able to detect oceans, continents, and atmospheric features from light years away. Direct imaging will transform the search for super-habitable worlds into a visual exploration of distant systems. The most exciting development in exoplanet research is atmospheric analysis. When a planet transits its star, some starlight passes through its atmosphere. This light carries the fingerprints of the gases in that atmosphere. Instruments like the James Webb Space Telescope analyze these spectral signatures to determine whether a planet has water vapor, carbon dioxide, methane, or oxygen. These molecules provide vital clues about temperature, climate, and potential life. For super-habitable planets, atmospheric analysis helps confirm whether conditions are mild, protective, and stable. A thick, balanced atmosphere could indicate a world more supportive of life than Earth. Another powerful tool is astrometry, which tracks the motion of stars across the sky. Tiny movements can indicate the presence of orbiting planets. Astrometry requires extremely precise measurements, but it can detect planets that other methods miss, especially large, nearby super-habitable candidates. As technology improves, astrometry may become one of the most important ways to find Earth-like planets close to our solar system. Infrared telescopes also play a major role in detecting planets around cooler stars. K-type and M-type stars emit much of their energy in infrared wavelengths. Instruments sensitive to infrared light can pick up subtle signals that optical telescopes miss. because many potentially superhabitable worlds orbit these cooler stars. Infrared observations help identify candidates with stable temperatures and long-term habitability. Machine learning and computational models have become essential tools in analysing exoplanet data. The massive amount of data collected by telescopes requires automated systems to identify patterns, correct errors, and filter out false positives. Machine learning helps distinguish real planetary signals from noise. It also helps predict which systems are most likely to host habitable or superhabitable worlds. These algorithms continuously improve as more planets are discovered, making the search faster and more accurate. Simulations also play an important role. Scientists use computer models to simulate planetary climates, atmospheres, and geological processes. These models estimate what conditions might exist on planets with certain sizes, compositions, and orbital distances. For superhabitable planets, simulations help determine whether shallow oceans, thicker atmospheres, or stronger magnetic fields are likely. They also show how life could evolve under different conditions. These simulations give scientists a window into environments we cannot yet observe directly. Space missions dedicated to exoplanet discovery continue to expand our knowledge. The Kepler mission revolutionized the field by discovering thousands of planets. The TESS mission is scanning nearly the entire sky for planets around nearby stars. The James Webb Space Telescope is analysing atmospheres with unprecedented detail. Future missions like the Nancy Grace Roman Space Telescope and ESA's Plato and Ariel missions will push these capabilities even further. Plato will search for Earth-sized planets around Sun-like stars with extreme precision. Ariel will focus on atmospheric characterization, helping identify superhabitable conditions. Ground-based observatories also contribute massively to exoplanet science. Telescopes like the Extremely Large Telescope, ELT, and the Giant Magellan Telescope, GMT, will gather more light and achieve higher resolution than any existing instruments. These observatories will allow scientists to study exoplanet atmospheres, surface temperatures, and even weather patterns. With enough sensitivity, they may detect clouds, storms, and seasonal changes on distant worlds. The ultimate goal is to detect biosignatures, signs of life. These include combinations of gases such as oxygen and methane present simultaneously, which on Earth indicate biological activity. Detecting such mixtures on a superhabitable world would be one of the greatest scientific discoveries in history. If we find these signs, they may point not just to life, but to life thriving under conditions superior to Earth's. Scientists also look for technosignatures, signals of advanced civilizations. These could include unusual radio patterns, infrared excess from artificial structures, or atmospheric chemicals that do not occur naturally. While these signals are speculative, the search continues because superhabitable planets could host older and more advanced civilizations. Life on these worlds might have had billions of extra years to evolve intelligence and technology. Another exciting approach is studying exomoons. Some moons around large planets may be habitable or even superhabitable. These moons could have stable climates due to tidal heating and magnetic protection. They may orbit gas giants within habitable zones, creating environments unlike anything seen in our solar system. Detecting exomoons is extremely difficult, but new methods may reveal them in the coming years. As we gather more data, scientists refine the criteria for superhabitability. These criteria include planet size, atmosphere thickness, magnetic field strength, star type, surface temperature, land-to-water ratio, and age. By comparing new exoplanets to these criteria, scientists can quickly assess their potential. Many planets discovered so far meet several criteria, and more discoveries are expected as detection tools improve. The search for worlds more habitable than Earth is not just technical, it is philosophical. It changes our view of Earth's place in the universe. It suggests that life-friendly worlds may be common. It raises the possibility that humanity is not alone, and it pushes us to imagine ecosystems, landscapes, and civilizations far beyond anything we know. The search continues because each new discovery brings us closer to understanding where life thrives best. Earth may be special to us, but the universe appears ready to show us worlds that surpass it. Life on super-habitable planets might evolve under conditions far more favourable than anything Earth has ever offered. Our planet supported life beautifully, but it did so through countless challenges, climatic extremes, mass extinctions, and geological disruptions. Life survived because it adapted, not because Earth was perfect. On a super-habitable world, the journey of evolution could be gentler, longer, and more stable. Life might spread faster, diversify earlier, and reach levels of complexity that Earth could never support. To imagine life on these planets, we must understand how small changes in environment can transform evolution on a planetary scale. The first major advantage for life on a super-habitable planet is the stability of climate. Earth's climate has fluctuated violently over its history. Ice sheets advanced and retreated, temperatures shifted dramatically. Entire ecosystems collapsed. Each cycle forced life to restart, recover, or disappear. A more stable planet would not subject life to such frequent setbacks. Mild temperatures spread across most of the surface would allow early life forms to emerge in more locations. They would not be limited to extreme environments or isolated pockets of habitability. When stability lasts for billions of years, life gains the opportunity to evolve continuously without interruption. Another important factor is the age of the planet. Many super-habitable worlds likely formed earlier than Earth and orbit stars that live longer. If a planet is 1 billion or 2 billion years older, life there may have evolved far beyond Earth's current stage. Evolution does not happen on a fixed schedule, but time is one of the most powerful tools life has. With billions of extra years, ecosystems could develop astonishing complexity. Species might diversify into forms Earth has never seen. Intelligence could emerge earlier and have more time to advance. Entire cycles of evolution, comparable to Earth's transition from microbes to multicellular life to animals, could have happened long before life on Earth reached insects. Shallow oceans on super-habitable planets could create environments that encourage rich biodiversity. On Earth, deep oceans trap nutrients and isolate ecosystems. Shallow seas allow sunlight to penetrate more efficiently, supporting more photosynthesis. They encourage the formation of coral-like systems, coastal wetlands, and nutrient-rich continental shelves. These regions are the most biologically productive environments on Earth, yet they make up only a small portion of the planet. A super-habitable world with large, shallow oceans would provide an immense amount of habitable surface area for marine life. If life begins in the oceans, as it did on Earth, a shallow world accelerates the path toward complex organisms. It also encourages earlier migration onto land if shallow regions form natural stepping stones. A thicker atmosphere on a super-habitable planet offers several benefits. It provides stronger protection from radiation, reducing the need for life to remain underground or underwater during early development. With less radiation damage, early organisms can evolve faster and more safely. A thick atmosphere also supports the development of larger organisms. On Earth, insects were once enormous during periods when oxygen levels were higher. A super-habitable planet with a slightly richer concentration of oxygen and stable air pressure could support gigantic plant-like structures and large complex animals. A thicker atmosphere also affects sound propagation, flight capability, and weather patterns. Life might evolve with features suited to denser air, such as broad wings, floating organisms, or species capable of gliding long distances. Stable tectonic activity also shapes evolution. Earth's plate tectonics helped create diverse environments, but also caused disasters. Massive volcanic eruptions, supercontinents forming and breaking, and shifts in ocean currents repeatedly disrupted life. On a super-habitable world, tectonics might be gentle and regular. This steady recycling of nutrients keeps ecosystems healthy without causing destructive global events. Continents might drift more slowly or remain stable for longer periods, allowing ecosystems to flourish without disruption. Stable continents mean stable coastlines, stable weather patterns, and long-lived habitats. Life would not need to constantly adapt to sudden planetary changes. The strength of a planet's magnetic field influences how life develops. A strong magnetic field protects the atmosphere from being stripped by stellar winds. It also reduces harmful radiation at the surface. On Earth, radiation influenced mutation rates, which in turn influenced evolution. On a superhabitable world, lower radiation does not stop evolution. It simply makes it safer and steadier. Life can evolve with fewer genetic bottlenecks or mass die-offs caused by radiation spikes. This increases the overall complexity and stability of biological development. Light plays an equally important role. Many super-habitable planets orbit K-type stars, which emit softer, more golden light than the Sun. This light penetrates atmospheres differently. Photosynthetic organisms might evolve pigments that harvest different wavelengths. On Earth, plants appear green because they reflect green light. On another world, alien plants could be red, purple, blue, or even black depending on the star's spectrum. Their efficiency could surpass Earth's photosynthesis. Better photosynthesis leads to more energy available to the food chain, supporting richer biodiversity. Land ecosystems on a super-habitable world might be more balanced than Earth's. Fewer deserts, fewer icy poles, and more temperate regions create a planet where life can spread almost everywhere. Earth's biodiversity is concentrated in a small number of ideal environments. A super-habitable planet could have far more ecosystems, each flourishing under stable conditions. Forests might dominate large regions. Grasslands or alien equivalents might stretch across continents. Swamps, wetlands, coastal zones, and island chains could interconnect into massive networks of life. Evolution on a world with fewer mass extinctions would be smoother and more continuous. Mass extinctions on Earth reset the evolutionary clock multiple times. Dinosaurs ruled for millions of years, but vanished in an instant due to an asteroid impact. Mammals surged in their absence. On a super-habitable planet with fewer catastrophic events, dominant species might persist much longer. Complexity would rise without being repeatedly knocked back. Instead of sharp evolutionary jumps, there might be more gradual but far more advanced development. Ecosystems would layer complexity upon complexity until reaching heights Earth might never see. Aquatic life, it could also evolve differently on a superhabitable world. Shallow oceans encourage a wide range of marine organisms. Coral-like structures could become massive. Reefs might stretch across entire coastlines. These environments act as biodiversity engines. They support thousands of species and serve as evolutionary testing grounds. On Earth, reefs have existed for hundreds of millions of years, but they collapsed repeatedly due to climate events. On a more stable planet, reefs could grow for billions of years uninterrupted. The diversity they produce could be extraordinary. Life in the air might also become more complex. If a planet has denser air and gentler winds, creatures with wings or wing-like structures might dominate large ecosystems. They might evolve incredible gliding abilities, floating capabilities, or energy-efficient flight. The sky itself might become an ecosystem full of life, unlike Earth, where only a fraction of species can fly. On a superhabitable world, airborne life could range from tiny drifting organisms to large, graceful flyers. Intelligent life is not guaranteed, but conditions on superhabitable planets improve the odds. Intelligence evolves when species have long-term stability, rich environments, abundant resources, and few existential threats. Earth's history is full of unpredictable disasters that nearly wiped out emerging intelligent species. On a superhabitable world with fewer catastrophes, intelligence might arise earlier and have more time to advance. Civilizations could develop technologies millions or billions of years before humanity existed. They might explore their planets, their solar systems, or even their galaxies long before Earth formed. The idea that superhabitable worlds could produce ancient, advanced civilizations is not science fiction, it's a realistic possibility. Life might also evolve in directions Earth cannot support. Higher oxygen levels could support larger organisms. Denser atmospheres could produce floating life similar to Earth's jellyfish, but airborne. Stable temperatures could allow cold-blooded organisms to grow unusually large. Mild oceans could support massive plant-like structures or giant reef networks. Life would adapt to whatever conditions exist, but those conditions might allow forms far beyond Earth's limits. Even microbial life might be more advanced. Microbes form the foundation of every ecosystem. On a stable planet, microbial evolution could produce complex biochemical pathways, highly efficient nutrient cycles, and ecosystems that recycle energy with incredible effectiveness. Earth's microbes faced countless extinction events, but microbes on a superhabitable world might evolve without interruption for billions of years longer. The landscapes of a superhabitable planet would reflect these biological possibilities. Forests might appear thicker, more intertwined, and more diverse. Oceans might sparkle with unfamiliar colours produced by photosynthetic organisms. Air might carry scents of alien forests and distant blooms. Life could fill every niche, from mountaintops to coastlines to open skies. The entire planet could be a living, breathing biosphere with complexity far beyond Earth's. Understanding how life might evolve on these planets also helps us understand our own future. Earth will not remain habitable forever. Studying superhabitable worlds gives us a glimpse of what life could achieve on planets with better natural advantages. It expands our imagination and prepares us for the possibility that the universe may contain ecosystems far richer than ours. Not all stars are equal when it comes to supporting life. Some stars burn too quickly, some explode too easily. Some bathe their planets in radiation. Others fluctuate so wildly that any nearby world would struggle to remain stable. Earth has survived around the Sun for billions of years, but even the Sun is not the perfect star for habitability. As scientists study the stars most likely to host planets more habitable than Earth, a clear pattern emerges. The best stars for life are not necessarily the brightest or most powerful. They are the most stable, gentle, long-lived, and predictable. The universe contains many such stars, and around them may orbit planets where life can flourish under ideal conditions. The Sun is a G-type star, sometimes called a yellow dwarf. It is larger and brighter than most stars in the galaxy. While it has supported life on Earth, it also presents several challenges. G-type stars tend to become brighter over time, slowly heating their planets. This long-term brightening will eventually make Earth uninhabitable. The Sun also emits strong ultraviolet radiation and produces solar storms that threaten satellites, astronauts, and electrical systems. While Earth's magnetic field protects us, these conditions are not ideal for long-term habitability. If Earth orbited a slightly different type of star, it might enjoy a more stable environment. Scientists believe that K-type stars, sometimes called orange dwarfs, are the best candidates for hosting super-habitable planets. K-type stars are slightly smaller and cooler than the Sun. They burn more slowly and remain stable for far longer. While the Sun will live for around 10 billion years, many K-type stars can shine steadily for 20 to 40 billion years or more. This extended lifespan gives planets more time to develop life. It also reduces the risk of abrupt changes in radiation levels or temperature. A planet orbiting in the habitable zone of a K-type star is likely to enjoy billions of years of calm conditions, more than enough time for life to evolve from simple organisms into complex ecosystems. K-type stars also emit less harmful ultraviolet radiation than the Sun. This softer radiation reduces genetic damage in early life forms. It allows complex organisms to thrive without needing extreme protective mechanisms. On Earth, UV radiation influences evolution, but it also poses dangers. A superhabitable world orbiting a K-type star would face fewer such threats, allowing life to spread more easily across land and oceans. The gentle light of an orange star might help ecosystems flourish more widely. Another advantage of K-type stars is that their habitable zones are closer in than those of G-type stars. This makes planets easier to detect using current methods. When a planet orbits closer to its star, it transits more frequently, providing more opportunities for measurement. It also exerts more gravitational pull, making radial velocity detection easier. Many of the best superhabitable planet candidates discovered so far orbit K-type stars. Their proximity and stability make them ideal locations for life. M-type stars, also known as red dwarfs, are the most common stars in the universe. They live even longer than K-type stars, trillions of years in some cases. However, their habitability potential is complicated. Red dwarfs often produce violent flares that blast nearby planets with radiation. Their habitable zones are extremely close, which increases tidal locking, a condition where one side of a planet always faces the star. This creates extreme temperature differences between the day and night sides. While some planets may still remain habitable due to thick atmospheres redistributing heat, many red dwarf systems have challenges that make habitability uncertain. However, not all red dwarfs behave the same way. Some become quiet as they age. If a planet forms orbiting a calm, older red dwarf, with reduced flare activity, it could become a strong candidate for superhabitability. A planet orbiting such a star would enjoy a long, stable window for life to develop. But because red dwarfs tend to strip atmospheres early in a planet's history, only the ones that avoid this problem remain candidates. F-type stars present the opposite challenge. These stars are larger and brighter than the Sun, but they're too short-lived. They burn through their fuel quickly, sometimes in just a few billion years. Life on Earth took around 4 billion years to reach complex forms. If Earth had orbited an F-type star, life might have run out of time before reaching its current complexity. F-type stars also emit stronger ultraviolet radiation, which can be harmful to early life. Although planets around F-type stars may appear Earth-like at first, their long-term potential is limited. They simply do not offer enough evolutionary time. The perfect stars for life seem to fall into a very specific category: stable, long-lived, and predictable. K-type stars fit this description well. They burn steadily, emit moderate energy, and maintain a gentle radiation environment. They give planets an extended opportunity to develop life uninterrupted. Superhabitable planets orbiting these stars could exist in great numbers throughout the galaxy. Because K-type stars are common, making up around 12% of all stars, there may be billions of such worlds. Another important feature of a star is its metallicity. In astronomy, metals refer to any element heavier than hydrogen and helium. Stars with higher metallicity are more likely to form rocky planets. Low metallicity stars may produce gas giants or fail to form planets altogether. Superhabitable worlds require rocky surfaces, oceans, and atmospheric chemistry. Therefore, stars with the right metallicity offer better chances for habitable planets. Many K-type stars meet these criteria, giving them a strong advantage. The variability of a star also matters. Some stars flicker or pulse in brightness due to internal processes. These changes can destabilize climates on orbiting planets. A star with stable brightness provides a consistent energy supply. Many of the stars associated with promising exoplanets are remarkably stable. This stability allows planets to remain in their habitable zones for billions of years without major changes. Even the star's magnetic activity influences habitability. Stars with strong magnetic fields produce more flares. These flares can strip planetary atmospheres, especially when planets orbit closely. K-type stars often have a gentler magnetic activity than both the Sun and red dwarfs. Their flares tend to be weaker, reducing the danger to nearby planets. These stellar characteristics shape the environments in which planets form. A superhabitable world requires a balance of energy, stability, and longevity. The star must provide enough heat to maintain liquid water, but not so much that the planet overheats. It must shine steadily without violent outbursts. It must live long enough for complex life to evolve. It must allow the planet to retain its atmosphere. Stars that meet these conditions give rise to worlds far more nurturing than Earth. Notably, some of the closest stars to Earth fit these conditions. Teegarden Star, for example, is a calm red dwarf that hosts two potentially habitable planets. Tau Ceti, a Sun-like star only 12 light-years away, has several super-Earths in its habitable zone. These systems offer valuable opportunities to study superhabitability. With upcoming telescopes, scientists may soon analyze their atmospheres for signs of life. Understanding the types of stars that support superhabitable planets is revolutionary because it expands our idea of where life can exist. Earth is a product of its star, but its star is not perfect. Better stars exist. Longer-lived stars exist, gentler stars exist, and around those stars may orbit planets capable of hosting ecosystems richer and more stable than ours. A planet's atmosphere is one of the most powerful forces shaping its habitability. It controls temperature, distributes heat, blocks radiation, carries moisture, and determines which forms of life can survive. Earth's atmosphere has supported billions of years of evolution, but it is far from perfect. It has fluctuated dramatically, carried dangerous levels of gases in the past, and still exposes life to harmful radiation. On a superhabitable world, the atmosphere could provide far better protection, stability, and nourishment than Earth's ever has. The difference between a habitable planet and a superhabitable planet is often written in its air. One of the clearest advantages a superhabitable planet may have is a thicker, more insulating atmosphere. Earth's atmosphere is thick enough to maintain liquid water and block harmful radiation, but it is thin enough that temperatures fluctuate sharply between night and day. A slightly thicker atmosphere would smooth out these fluctuations. Nights would stay warmer, days would be less harsh, and climate zones would be more consistent. Life would not need to adapt to extreme temperature differences. Ecosystems could flourish in regions that on Earth are deserts or frozen wastelands. A thicker atmosphere also improves protection from cosmic radiation. Earth's magnetic field helps, but even with this shield, some radiation reaches the surface. On a superhabitable planet, the combination of a stronger magnetic field and a denser atmosphere could reduce radiation to nearly negligible levels. This would benefit life enormously. Early life wouldn't need to hide underwater or underground. Complex organisms would suffer fewer mutations caused by radiation damage. Lifespans might be longer, reproduction safer, and evolutionary pathways smoother. Another important factor is atmospheric composition. Earth's oxygen levels have fluctuated wildly throughout history. There were times when oxygen was too low for complex life, and times when it was dangerously high. High oxygen levels can cause fires and increase oxidative stress in organisms. A superhabitable world would likely have a balanced oxygen level, slightly higher than Earth's current level, but not dangerously high. This would support more energetic metabolisms and allow larger or more active species to evolve. Evolution could unfold faster, simply because organisms could generate more energy from their environment. Carbon dioxide levels also matter. Too much CO2 creates runaway greenhouse effects. Too little causes global freezing. Earth has struggled to maintain CO2 balance, relying on tectonic cycles to regulate it. A superhabitable world might have more efficient natural balancing mechanisms. For example, a world with more shallow seas might absorb and release CO2 more steadily. A thicker atmosphere with balanced greenhouse gases could maintain mild temperatures across most of the surface, reducing climate extremes and keeping the planet stable for billions of years. Water vapor is another essential component. On Earth, water vapor is unevenly distributed, contributing to deserts, monsoons, droughts, and unpredictable weather patterns. Superhabitable planets might have more uniform water cycles. A denser atmosphere could hold more moisture, creating widespread cloud cover that shields the surface from harmful rays and stabilizes temperature. More moisture means more rain, more rivers, more wetlands, and more ecosystems where life can thrive. Atmospheric pressure also influences evolution. Higher pressure allows liquids to remain stable over a wider range of temperatures. It also helps organisms retain body moisture. On a superhabitable planet, slightly higher pressure would support diverse life forms, including species adapted to dense air. Flying creatures could glide more easily, sound would travel more efficiently, seeds and spores could disperse farther, even plant-like organisms could grow larger in denser atmospheres due to better gas exchange. Another key atmospheric factor is the absence of toxic elements. Earth's early atmosphere contained methane, ammonia, sulfur dioxide, and other dangerous gases that prevented complex life from evolving for billions of years. Even today, volcanic eruptions inject harmful gases into the atmosphere, affecting climate and life. A superhabitable planet might have fewer volcanic toxins or more efficient atmospheric cleansing processes. Its air could remain stable and clean for long stretches of time. Life would face fewer harsh chemical environments and more consistent conditions. The planet's star also influences its atmosphere. K-type stars emit softer, more gentle radiation than the Sun. Their ultraviolet output is lower, reducing atmospheric erosion and allowing more stable atmospheric layers to form. On Earth, the ozone layer protects from UV radiation, but this layer formed only after billions of years of evolving oxygen-producing life. A superhabitable planet under a calm star may not need such a complex protective mechanism. Cloud cover is another important atmospheric feature. Too much cloud cover cools a planet. Too little heats it up. On Earth, cloud patterns are uneven and unpredictable, but on a superhabitable world with a thicker atmosphere, cloud systems might be more stable and widespread. The right type of cloud cover shields the surface from harmful rays but allows enough light for photosynthesis. This balance creates a comfortable global environment. Even tropical zones could be mild and livable. Wind patterns would also behave differently. Earth's winds are shaped by temperature differences between the equator and the poles. Because Earth has strong climate zones, winds can be harsh, unpredictable, and destructive. On a superhabitable planet with milder temperature differences, winds might be gentler and more consistent. This could influence plant evolution, animal migration, and ocean currents. A calmer atmosphere supports richer ecosystems and reduces the risk of extreme weather events. One of the most fascinating atmospheric possibilities is the presence of greenhouse gases in perfect balance. Earth struggles with CO2 regulation. Too much CO2 causes warming, too little causes cooling. Superhabitable planets might have long-lasting natural feedback systems that keep greenhouse gases stable. This stability would create a climate that remains within a narrow temperature range for billions of years. Life would not need to adapt to extreme heat waves or ice ages. It could evolve steadily. Even the colour of the sky on a superhabitable world could influence evolution. The atmosphere determines how light scatters. A thicker atmosphere with different gas mixtures could produce deeper blues, pale greens, or even golden skies. These colours affect how organisms develop vision and how plants evolve pigments. Light spectrum shapes biology in ways we often overlook. On some worlds, photosynthesis might use different wavelengths, producing forests of unfamiliar colours. Weather patterns also differ on superhabitable worlds. Earth's storms can be powerful and destructive, shaped by strong temperature contrasts. A planet with more uniform temperatures has less violent weather. Rainfall might be gentle and consistent. Storms might be smaller and shorter-lived. This would prevent environmental damage and allow delicate ecosystems to survive in places where Earth's storms would destroy them. Calm weather also encourages plant growth and supports large herbivores, similar to how Earth's mild regions support the greatest biodiversity. Atmospheric longevity is another key difference. Earth's atmosphere is slowly evaporating into space. although very slowly. A superhabitable planet with a stronger magnetic field and thicker air may retain its atmosphere for far longer. Atmospheric loss slows significantly when a planet has strong protection. This allows life to remain stable over immense spans of time. Even atmospheric chemistry can promote or hinder life. Earth's atmosphere has only recently reached a state suitable for advanced life. Before that, it was unstable and toxic for billions of years. A superhabitable planet might have reached chemical equilibrium much earlier, allowing life to evolve for a longer period. The atmosphere could be tuned naturally to support organic molecules and energy cycles that promote biological growth. The role of weathering cycles on rocks also affects habitability. On Earth, atmospheric CO2 reacts with rocks, removing CO2 from the atmosphere. This regulates climate but can cause cooling periods. A superhabitable world with more balanced rock composition or smoother tectonics might regulate CO2 more efficiently, preventing extreme cooling or heating periods. This maintains a stable climate where life thrives continuously. Even atmospheric pressure affects water evaporation. On Earth, evaporation varies widely, affecting climate patterns. A superhabitable planet with a pressure level optimized for slow, consistent evaporation would have long-lasting lakes, rivers, and wetlands. These environments are ideal for life, creating continuous water availability across large areas. Lastly, the atmosphere influences sound, smell, and sensory evolution. A denser atmosphere could allow larger animals to communicate over longer distances. Plants might release different chemical signals. Animals could evolve advanced sensory systems suited to richer atmospheric environments. These differences could drive evolution in unique directions, leading to ecosystems Earth has never seen. When scientists imagine a superhabitable world, they often imagine a sky thicker and softer than Earth's, with gentle winds, mild seasons, stable temperatures, and rich atmospheric chemistry. Life would experience fewer existential threats and more opportunities to flourish. The air itself would become a supportive medium that nurtures life at every stage. Water is the foundation of life as we know it, and the way water behaves on a planet determines how rich, diverse, and stable its ecosystems can become. Earth's oceans helped life begin, but they also limit it in many ways. Our deep oceans hide nutrients beneath crushing pressure. Our coastlines are narrow compared to the size of the continents. Our freshwater systems are unevenly distributed, and our ice-covered poles lock away vast amounts of water and land. But on a superhabitable planet, one designed by nature with more balanced conditions, water may flow, gather, and circulate in ways that create far more diverse environments than Earth ever could. Water shapes life, and on a more perfect world, it could shape life to astonishing levels. One of the biggest advantages a superhabitable planet may offer is shallow global oceans. On Earth, the average depth of the ocean is nearly 4 kilometers, which prevents sunlight from reaching most of the ocean floor. This limits photosynthesis, which in turn limits the number of ecosystems that can exist. In the deep ocean, life survives but cannot expand easily. Sunlight only feeds a thin layer near the surface, but on a world where oceans are much shallower, sunlight penetrates everywhere. Entire seas become illuminated ecosystems. Plants or plant-like organisms could grow across enormous stretches of ocean floors, creating underwater forests, reefs, and plains far richer than anything on Earth. Shallow oceans transform a planet into one giant cradle for life. The coastline regions of a superhabitable planet would also be more extensive. On Earth, coastlines form only where land and sea meet at just the right elevation. These regions are incredibly productive because they mix nutrients from land with nutrients from the ocean. But Earth simply does not have enough coastline to maximize biodiversity. A superhabitable planet with widespread shallow seas, gentle slopes, and stable sea levels would have coastlines stretching across continents in complex networks of bays, lagoons, deltas, and wetlands. These environments support life in layers: water, land, and air, all interacting in dense biological webs. A world with 10 times more coastline than Earth might support 10 times more species simply because more ecological niches exist. Freshwater systems would also behave differently on such a planet. Earth's rivers and lakes are shaped by uneven climates, mountain-building events, and unpredictable rainfall cycles. Many regions on Earth are dry simply because geography prevents moisture from reaching them. But on a superhabitable planet with milder climates and a thicker atmosphere, evaporation and rainfall could become more evenly distributed. Rivers could be larger, more stable, and flow more consistently. Rainforests could stretch much farther. Wetlands could cover vast continental interiors instead of being confined to narrow regions. More freshwater means more places where life can flourish, evolve, and diversify. Glaciers and ice caps present another limitation on Earth. Our planet traps enormous amounts of water as ice at the poles. These regions are largely uninhabitable. They store water instead of circulating it, locking away potential habitats. A superhabitable planet might have smaller polar regions or none at all. If temperature ranges are mild across the globe, large ice caps may never form. Without massive ice sheets draining moisture and covering land, more surface becomes available for ecosystems. A planet without frozen deserts would naturally support more biodiversity. Another key factor is the motion of water. Earth's oceans circulate through complex currents driven by temperature differences, salinity, and rotation. These currents influence climate and nutrient distribution. However, they also create unstable patterns such as El Niño and La Niña, which disrupt ecosystems. On a superhabitable planet with more consistent climates, ocean currents might be gentler and more predictable. This would allow marine ecosystems to remain stable for longer periods, reducing stress on species and encouraging long-term evolutionary growth. Consistent ocean circulation also distributes nutrients more evenly, supporting richer marine life. Tides also shape life. On Earth, tides are influenced by the moon. If a superhabitable planet has more than one moon or a larger moon, tides could be stronger and more dynamic. Stronger tides could create larger tidal zones, which are incredibly productive ecosystems. Tidal flats, estuaries, and mangrove-like coastal regions could expand dramatically. These environments serve as nurseries for marine life. Larger, more dynamic tidal ecosystems mean more opportunities for evolution. But tides must not be excessively extreme, or they would become destructive. Superhabitable planets may have ideal balance, strong tides that enhance life without destabilizing coastlines. The chemistry of water also matters. Earth's oceans contain salts and minerals that support life, but their concentration has changed over time. On a superhabitable world, ocean chemistry may be more uniform or optimized for biological processes. More balanced mineral levels help organisms develop shells, bones, and other structures more efficiently. Some planets may even have oceans rich in nutrients that Earth's water lacks. If nutrients are abundant and evenly spread, life can emerge everywhere rather than in isolated pockets. Volcanic activity under the oceans also influences habitability. On Earth, hydrothermal vents provide energy for unique ecosystems. But Earth's volcanic activity is unpredictable and violent. A superhabitable planet might have mild but widespread underwater volcanic activity, just enough to create energy sources without causing mass extinctions. These gentle energy gradients could support diverse chemical reactions that enable life to thrive in the deep ocean as well as the shallow seas. The presence of small islands scattered throughout the oceans also supports biodiversity. Islands encourage species to evolve in isolation. On Earth, island ecosystems produce some of the strangest and most unique species. Think of the Galapagos or Madagascar. A superhabitable planet with many small islands across shallow oceans would act as a natural laboratory for evolution. Species would adapt to different environments, creating a mosaic of life forms. Over time, isolated populations could diverge into completely different species, increasing overall biodiversity dramatically. Water interacts with atmosphere as well. On a superhabitable planet, the balance between ocean evaporation and rainfall might be more stable. This stability supports consistent weather patterns that nourish ecosystems. Rainfall that comes gently and regularly supports forests, grasslands, and wetlands. A smoother water cycle reduces the risk of droughts and floods. Life gains more secure footing in these stable climates. Even the colour of oceans can affect habitability. On Earth, ocean colour comes from pigments in phytoplankton. On a superhabitable world with more efficient photosynthesis, oceans may be darker, greener, or richer in pigments. These oceans would absorb more sunlight and support thicker layers of marine life. The energy captured by oceanic photosynthesis forms the base of the food chain. A world with enhanced photosynthetic efficiency could support ecosystems far larger and more complex than Earth's. Another important factor is how water shapes land. Rivers carve valleys, deposit minerals, and create fertile soil. On Earth, this process is uneven. Some regions are fertile while others are barren. On a superhabitable world with more uniform rainfall and gentler tectonics, erosion and deposition might produce fertile plains across much wider areas. This soil richness would support vast forests, meadows, and plant ecosystems. More fertile land means more food, more niches for organisms, and greater diversification. A crucial aspect of water-based habitability is the time it remains stable. Earth has experienced dramatic shifts in sea level, sometimes rising hundreds of meters and drowning coastlines. On a superhabitable planet with a more stable climate, sea levels might change very slowly. Stable coastlines support long-term evolution. Forests, wetlands, and marine nurseries can exist for millions or billions of years without interruption. Even the boundaries between land and ocean influence evolution. On Earth, the transition zones, beaches, marshes, deltas, are rich in life because they mix nutrients from land and sea. A superhabitable world with more shorelines produces more of these transitions. Life thrives where different environments intersect. More intersections mean more niches, more species, and more adaptive variations. Salt concentration is another factor. If oceans are slightly less salty than Earth's, organisms may evolve with fewer physiological limitations. Salt concentration impacts osmosis, hydration, and metabolism. Lower salinity allows larger organisms to evolve more easily. Higher salinity restricts biodiversity. Superhabitable oceans may sit at the perfect balance for life. Superhabitable worlds may also avoid extreme water losses. Earth loses water to space slowly over time. A planet with a stronger magnetic field and more protective atmosphere would retain water far longer. More water retention means long-term ecosystems that do not dry out. Life has time to flourish without facing extinction due to water loss. Water also influences temperature. Oceans absorb heat and distribute it globally. A superhabitable planet with shallow, widespread oceans would regulate its climate better than Earth. Temperature extremes would shrink. Climate zones would blend. This uniformity creates ideal conditions for life to thrive in more regions. Finally, water shapes evolution by offering safety. Oceans protect early life from radiation, asteroids, and temperature swings. On a superhabitable planet with calmer oceans, early life might spread faster, diversify more easily, and move onto land sooner. Evolution would accelerate simply because water offers safety and stability. On such worlds, oceans, lakes, rivers, and wetland networks become the arteries of life, constantly flowing, nourishing, and shaping biological diversity. The water cycle becomes a steady engine supporting millions of interconnected species. The structure of a planet determines how long it can stay habitable, how stable its environment remains, and how diverse its ecosystems can become. Earth's geology has supported life for billions of years, but it has also caused massive disruptions. Supervolcanoes, shifting continents, violent earthquakes, and sudden climate swings have pushed life to the edge repeatedly. On a superhabitable world, geology may behave differently, smoother, gentler, more stable, and more supportive of life. The deeper we look at how planets form and evolve, the clearer it becomes that geology may be one of the most important factors separating an ordinary, habitable world from a truly superhabitable one. One of the biggest geological differences involves plate tectonics. Earth's tectonic plates drift across the surface, creating mountains, volcanoes, and ocean basins. This movement recycles carbon, regulates climate, and provides nutrients. But Earth's tectonics are also violent. Entire regions can be devastated by earthquakes. Supervolcanoes can release enough ash to cool the planet for years. Continents collide, separate, and reform in ways that dramatically alter ecosystems. A superhabitable planet would likely have tectonic activity, but it would be milder and more consistent. Instead of sudden eruptions and destructive earthquakes, the crust might shift slowly and steadily. This would maintain the essential climate regulation that tectonics provide, but avoid the catastrophic events that reset evolution. The size of a planet deeply influences its geology. Earth is large enough to maintain a molten core and active tectonics, but small enough to lose heat steadily. A superhabitable planet might be slightly larger, perhaps 10 to 20% bigger. This size increases internal heat, which keeps tectonics active for longer without becoming too violent. A larger world also supports a stronger magnetic field, protecting the surface from harmful radiation. The combination of a warm interior and strong magnetic field creates a stable foundation for life. On Earth, our magnetic field sometimes weakens or flips, exposing the planet to increased radiation. A superhabitable planet with a larger, more stable core would avoid such vulnerability. Continental structure is another defining factor. Earth's continents drift and change shape over millions of years, often forming supercontinents. Supercontinents create extreme interior climates, dry, hot, and hostile to life. When they break apart, sea levels rise, coastlines flood, and ecosystems must adjust. A super habitable world might have smaller, more numerous continents distributed more evenly across the planet. This arrangement avoids massive supercontinents and creates a higher ratio of coastlines, which are among the most life-rich environments. More continents mean more climates, more habitats, and more evolutionary opportunities. Earth's uneven landmass distribution limits biodiversity by clustering life into certain regions. A world with balanced continents could support far more species. The surface shape also influences habitability. Earth has high mountain ranges, deep trenches, and steep geological contrasts. While these create stunning landscapes, they also create uninhabitable extremes. A super habitable world might have gentler slopes at moderate mountain ranges and fewer extreme elevations. This would expand habitable land area and reduce environmental stress. Millions of square miles of Earth are too cold, too high, or too steep for significant life. On a smoother, more balanced world, more of the surface becomes livable. Volcanism is another major factor. Earth's volcanoes play an essential role in recycling carbon and supplying nutrients, but volcanic eruptions can release massive amounts of ash, sulfur, and CO2, triggering climate change. Some eruptions in Earth's past led to mass extinctions. On a super habitable planet, volcanic activity might be more evenly distributed and less explosive. Instead of giant eruptions, the planet might experience frequent but mild volcanic activity. This would maintain nutrient cycles without destroying ecosystems. Stable volcanism also supports fertile soils, boosting plant growth and overall biodiversity. The composition of the crust matters as well. Earth's crust varies widely in mineral content. Some areas are rich in nutrients, while others are barren. A super habitable planet's crust might contain more evenly distributed minerals. This would allow plant-like life to spread more easily and support broader ecosystems. Nutrient-rich soils encourage complex food webs and diverse species. On Earth, highly fertile regions like river deltas and volcanic soils become biodiversity hotspots. A superhabitable planet with uniformly fertile crust could make the entire biosphere flourish. Water flow is also shaped by geology. Earth's rivers depend on mountain systems and rainfall cycles, which vary greatly. Some regions are lush while others remain deserts for millions of years. A superhabitable planet with gentler slopes and more consistent rainfall would create widespread networks of rivers, lakes, and wetlands. These water systems form evolutionary corridors where species migrate, diversify, and interact. A world with interconnected water systems provides life-abundant opportunities to evolve across different environments. Another important geological aspect is the longevity of the planet's interior heat. Earth's core is gradually cooling. Eventually, tectonic activity will slow, and the magnetic field will weaken. When that happens, Earth will lose its protective shield, and life will face greater threats. A superhabitable world with a slightly larger mass would retain its interior heat for much longer. This means tectonics, volcanism, magnetic protection, and atmosphere regulation could continue far beyond Earth's lifespan. Stability over tens of billions of years is possible. Such long-term geological health creates ideal conditions for deep, uninterrupted evolution. Hydrothermal systems also influence habitability. On Earth, deep-sea vents provide environments where life thrives without sunlight. These ecosystems may resemble the earliest life forms on Earth. A superhabitable planet with widespread mild hydrothermal activity could support rich microbial ecosystems across ocean floors. These pockets of energy and chemistry become sources for biological diversification. If hydrothermal systems are stable and abundant, early life gains more opportunities to emerge and evolve. Geology also determines how planets recover from disasters. On Earth, asteroid impacts reshaped the planet repeatedly. Craters formed, dust blocked sunlight, and ecosystems collapsed. A superhabitable planet might orbit a star in a system with fewer asteroids or a more stable gravitational arrangement. Fewer impacts mean fewer mass extinctions. This gives life uninterrupted time to evolve into higher forms. Even if impacts occur, a thicker atmosphere or stronger magnetic field could reduce their effects. Some superhabitable planets might even orbit stars in quiet cosmic neighborhoods with minimal debris. Another geological factor is soil formation. Earth's soils took millions of years to develop, and erosion constantly reshapes them. On a superhabitable planet with mild weather, consistent rainfall and fertile crust, soil could form faster and remain stable longer. Stable soil supports rich plant life, which in turn supports animal life. On Earth, deserts cover 1/3 of the land. A superhabitable planet with fewer deserts and more fertile landmass could support ecosystems everywhere, not just in select regions. The chemical composition of rocks also shapes life. Rocks interact with water and atmosphere to produce nutrients essential for evolution. A superhabitable world might have rock compositions that release nutrients more easily. This would allow life to spread rapidly and diversify. Regions that on Earth are barren, like mountain peaks or rocky deserts, could become fertile on another world if the geology is more favourable. Internal planet structure also affects surface stability. Earth's mantle convection drives tectonics, but it also triggers earthquakes and volcanic eruptions. A superhabitable planet might have a more uniform mantle temperature. This would produce gentler tectonic motion without violent quakes. A planet with fewer seismic disruptions would allow forests, reefs, and species to grow without being wiped out by geological events. The thickness of the crust is another key factor. A thicker crust can prevent excessive volcanism, while a thinner crust supports more gentle heat flow. The perfect thickness lies somewhere between Earth's extremes. A balanced crust creates a stable surface without choking tectonics or causing excessive volcanic activity. Many superhabitable candidates likely have crusts in this ideal zone. Geology even influences climate indirectly. Mountain ranges block airflow and create deserts. Ocean basins determine currents. Volcanic gases influence greenhouse levels. Tectonics shape coastlines. A superhabitable planet's geological structure would create climates that are mild, predictable, and globally connected. This increases habitable surface area and reduces climate extremes. The final geological factor is longevity. Earth's geological activity will eventually cease, and when it does, habitability will decline. A superhabitable world could remain geologically active for much longer, maintaining natural climate regulation and nutrient cycling over timescales far exceeding Earth's lifespan. This extended geological health gives life vast periods to evolve, diversify, and perhaps reach intelligence. Understanding geology helps us recognize how planets become superhabitable. It reveals that Earth's crust, continents, tectonics, and internal heat are not the perfect balance for life. They are simply adequate. Better worlds exist where geology works in harmony with atmosphere, water and climate to create long-lasting stability. On such worlds, life could reach heights we can barely imagine. Habitability is not a permanent condition. It shifts, evolves, strengthens, and fades over time. A planet may begin as a lifeless rock, transform into a paradise, flourish for billions of years, and eventually decline into an inhospitable world. Earth has passed through many phases of habitability, some stable and others chaotic. In the early years, the planet was volcanic and violent. Later, it became a water world filled with microbial life. Eventually, it grew forests, animals, and intelligent species. But none of these phases lasted forever. If we want to understand superhabitable planets, worlds that may support life better than Earth, we must understand how habitability evolves across immense stretches of time. Some planets remain in their most life-friendly phase, far longer than Earth ever could. Others have conditions that continue improving instead of declining. Time becomes the single greatest advantage a planet can offer life. Earth's timeline began with millions of years of intense bombardment from asteroids and comets. This era boiled oceans, destroyed forming atmospheres, and melted surface rocks repeatedly. Only after this violent phase subsided did life have a chance to begin. But even once life emerged, Earth's environment was still unstable. The young sun emitted strong radiation. The atmosphere lacked oxygen. Volcanoes reshaped the land, and the oceans were filled with hazardous chemicals. It took billions of years for Earth to reach a stable balance that supported large, complex organisms. This long delay highlights Earth's weakness. Life here had to struggle through conditions that were far from ideal. On a superhabitable planet, the story might unfold differently. If the planet formed earlier than Earth, or around a star that was stable from the beginning, life could emerge much sooner. Instead of waiting billions of years for the atmosphere to become safe, life could evolve immediately under mild conditions. A stable star with gentle radiation would not strip atmospheres or sterilize surfaces. Early oceans would remain calm. Surface temperatures would settle quickly. Habitability would begin early and continue uninterrupted. That early head start could grant life enormous evolutionary time. Species on such a planet might have existed for billions of years, longer than anything on Earth. The length of the star's lifetime plays a central role in habitability. The sun will remain stable for a few more billion years before growing hotter and turning Earth into a dry, uninhabitable world. In contrast, K-type stars can remain stable for tens of billions of years. Their habitable zones shift far more slowly. Planets orbiting these stars can enjoy long-lasting stability. Life on these worlds has time, a resource Earth cannot provide forever. Time allows for deeper evolution, greater biodiversity, and potentially the rise of intelligent civilizations long before Earth's timeline would permit such complexity. Habitability also changes as a planet cools internally. Earth's internal heat drives tectonics, volcanism, and magnetic fields. Over billions of years, Earth's core slowly cools. Eventually, tectonic activity will cease, the magnetic field will weaken, and the atmosphere will become more vulnerable. Habitability will decline gradually as oceans shrink, climates destabilize, and radiation increases. Earth's long-term decline is inevitable, but a slightly larger, more stable planet would cool more slowly. It could maintain tectonics and magnetic fields for tens of billions of years. This extended geological lifespan helps sustain habitability far beyond Earth's limits. Another factor is atmospheric evolution. Earth's atmosphere changed dramatically over time. Early Earth had almost no oxygen. Later, it had too much carbon dioxide. Even today, fluctuations pose climate risks. On a more balanced planet, atmosphere composition might stabilize early and remain steady. The climate would evolve gently without catastrophic shifts. Life would not face repeated extinction cycles. Instead, ecosystems would grow continuously, layering complexity upon complexity without interruption. Water availability also changes with time. On Earth, oceans formed early, but may eventually evaporate as the sun brightens. As temperatures rise, oceans will shrink, humidity will increase, and greenhouse effects will accelerate. Earth's water cycle will collapse. A super-habitable world orbiting a less rapidly brightening star would avoid this fate. Its oceans could remain liquid for far longer. Stable oceans create stable climates, supporting life for epic timescales beyond Earth's lifespan. Even the shape and position of continents evolve with time. Earth's continents drift, merge, and break apart. These movements trigger ice ages, change ocean currents, and alter climate patterns dramatically. Each cycle reshapes habitability. On a super-habitable world, continental drift might be slower and more stable. Instead of forming supercontinents that cause extreme climates, the land masses may remain distributed evenly for billions of years. Stable land distribution ensures long-term habitats that allow life to evolve smoothly. Another time-dependent factor is mass extinction events. Earth experienced at least 5 major extinctions that wiped out large fractions of life. Each event was triggered by a planetary or cosmic catastrophe: asteroids, volcanic eruptions, climate shifts. These wiped out dominant species and reshaped ecosystems. On a super-habitable world, in a more peaceful cosmic neighborhood, with fewer asteroids or fewer violent geological events, extinction cycles may be rare or mild. This allows life to diversify steadily instead of repeatedly restarting. Over billions of years, uninterrupted evolution produces ecosystems of unimaginable complexity. Habitability also depends on how energy from the star changes over time. The sun brightens slowly but significantly. Earth's habitability window is limited because of this. K-type stars brighten far more slowly. Their energy output remains stable for tens of billions of years, creating long-term environments where habitability does not decline rapidly. Planets orbiting these stars do not face the same heat-driven end that Earth does. Their atmospheres do not evaporate as quickly. Their climates do not collapse suddenly. Life gains more time to evolve, adapt, and expand. Even seasons change with time. Earth's tilt varies, causing ice ages and temperature swings. Over millions of years, these cycles shift habitability patterns. On a super-habitable planet with a more stable tilt, seasons could remain consistent for billions of years. This stability encourages long-term ecosystem growth. Life does not need to constantly adjust to new climate extremes. Instead, species adapt to steady environments that allow deeper evolutionary developments. Magnetic fields also evolve. Earth's magnetic field reverses occasionally. During reversals, radiation levels rise. These periods do not sterilize the planet, but stress life. A super-habitable world with a stronger or more stable magnetic field avoids these fluctuations. Its surface remains shielded over long time scales. This allows organisms to evolve without radiation-driven setbacks. The mineral composition of a planet evolves too. On Earth, minerals available to early life were limited. Over billions of years, biochemical diversity increased. On a superhabitable world, mineral evolution might progress faster due to more favourable geology. Mineral diversity promotes biochemical diversity, helping life explore more evolutionary pathways earlier in planetary history. Habitability also depends on orbit stability. Earth's orbit is relatively stable, but small changes can influence long-term climate. A superhabitable planet might have a more circular orbit that varies even less over time. This would minimize climate fluctuations and extend the duration of ideal conditions. A world that never strays far from perfect temperatures remains habitable for longer spans. Even the presence of moons changes with time. Earth's moon stabilizes our tilt, but it is slowly drifting away. Over billions of years, this will weaken its stabilizing effect. On a superhabitable world, moons might remain in stable orbits indefinitely. Some planets could have multiple moons that strengthen and tilt stability. This prevents extreme seasonal shifts and maintains long-term climate consistency. Beyond physical factors, the timeline of life itself evolves differently depending on environmental conditions. On Earth, life's progress was repeatedly interrupted. On a superhabitable world, life may reach each evolutionary milestone earlier. Microbial life might appear quickly, followed by multicellular organisms, land colonization, animal diversification, and possibly intelligence. Because evolution would not restart due to mass extinctions, each stage might be reached faster and progress deeper. Advanced ecosystems could exist early in the planet's life and continue improving for billions of years. This raises the possibility that some planets in the universe may host ancient ecosystems far older than Earth's. If Earth's oldest complex life is a few 100 million years old, another planet might host complex life billions of years old. Their ecosystems might appear alien, yet incredibly developed. Giant forests, vast reef networks, complex food webs, and highly specialized species that refine their traits over immense timescales. Habitability also fades differently depending on the planet. Earth's future is limited by the sun's brightening. Superhabitable worlds orbiting long-lived stars might avoid this fate for tens of billions of years. Their habitability declines slowly, giving species ample time to adapt. Some worlds may transition into new forms of habitability, cooling over time and reshaping ecosystems instead of collapsing into extinction. Understanding habitability over billions of years helps us appreciate how rare Earth truly is in one sense, but also how common better planets might be. Earth gave life a chance despite its limitations, but somewhere in the universe, there may be planets where habitability peaked long ago and remains perfect even now. Time is the universe's greatest tool for creating advanced life. And on worlds with more stability, more balance, and more longevity than Earth, the story of life may be vastly richer. Discovering planets more habitable than Earth forces us to rethink everything we know about life, our planet, and our place in the universe. For centuries, humanity believed Earth was the center of habitability, the one world designed for life. We imagined our planet as rare, delicate, and incomparable, but the discovery of superhabitable worlds, planets potentially better suited for life than Earth, reshapes that belief entirely. It reveals that Earth may not be special because it is perfect, but because it is one of many possible homes for life. This realization does not diminish Earth. Instead, it elevates the universe. It suggests that the cosmos is richer, more fertile, and more welcoming to life than we ever imagined. The first major shift is understanding that habitability is is not limited to Earth-like conditions. Earth provides life with just enough resources to survive, but not always enough to thrive. Our planet has faced ice ages, volcanic winters, meteor impacts, radiation bursts, and climate chaos. Life endured because it adapted to Earth's imperfections. On a super-habitable world, life might not face such adversity. It could flourish under ideal temperatures, stable climates, thick protective atmospheres, and oceans teeming with nutrients. The idea that Earth is not the best possible environment is humbling. It shows us that the universe may contain countless worlds where life could flourish far beyond Earth's biological limits. The second shift comes from recognizing how many of these worlds might exist. Super-habitable planets are not rare exceptions. They could be common features of the galaxy. Many orbit K-type stars, long-lived stable stars that offer billions more years of gentler light than our Sun. These stars are abundant, meaning the galaxy may contain billions of planets better suited for life than Earth. If even a fraction of them host oceans, continents, and atmospheres optimized for life, then the universe is overflowing with biological potential. The idea that Earth is unique fades in the face of overwhelming possibility. Habitable environments may be the rule, not the exception. The discovery of these worlds also changes how we think about evolution. On Earth, evolution was interrupted constantly. Mass extinctions destroyed entire branches of life. Catastrophic climate swings erased species before they could diversify. On a super-habitable world with fewer crises, evolution could proceed faster and more steadily. Complex organisms might appear sooner, ecosystems might grow richer, and intelligence might emerge earlier. This means that somewhere in the universe, advanced life could exist, not because it is rare, but because its planet provided the perfect environment for billions of years. Earth's evolutionary timeline may be slow compared to planets with gentler histories. Understanding super-habitable worlds also changes the way we search for life beyond our solar system. Instead of looking only for Earth-like planets, scientists now search for worlds that exceed Earth's conditions. These are the planets that offer the best chance of finding life. Not worlds struggling at the edge of habitability, but worlds thriving at its centre. This shift broadens the scope of our exploration. It pushes science to develop better telescopes, more sensitive instruments, and more ambitious missions. The search becomes not just a quest to find another Earth, but to find something better than Earth. This discovery also changes how we view our own future. Earth will not remain habitable forever. The sun will grow hotter, the oceans will evaporate, the atmosphere will collapse. But if planets more habitable than Earth exist, they represent potential futures for humanity. They show us that survival beyond Earth is not science fiction. It is a natural extension of life's desire to thrive. These worlds may be far away, but knowing they exist helps us imagine long-term survival beyond our solar system. They become destinations for future generations, symbols of hope rather than distant fantasies. At a deeper level, discovering super-habitable worlds forces us to confront our cosmic humility. We have long believed Earth is exceptional, but the universe may be filled with planets that surpass it. This humbling perspective reminds us that life is not limited to a single blueprint. It adapts, spreads, and thrives wherever conditions allow. If super-habitable planets host ecosystems older, richer, and more complex than ours, then the universe may already be full of life. Not primitive microbes, but advanced species living under gentle suns on stable worlds. The emotional impact of this discovery is profound. It tells us we are part of something bigger, a universe that encourages life rather than resisting it. Instead of being alone, we might be late to the cosmic party. Other worlds may have birthed civilizations before Earth formed. Their histories might span billions of years longer than ours. Their cultures, technologies, and knowledge may have advanced far beyond our imagination. The possibility that life thrives under better conditions challenges us to expand our perspective beyond Earth's narrow boundaries. This discovery also deepens our appreciation for Earth's uniqueness. Earth may not be the most habitable world, but it is our home, the planet where life evolved against all odds. Earth's imperfections shaped us. Its struggles forged our resilience. Its challenges forced us to innovate. If we discover planets that surpass Earth, it does not diminish Earth's value. Instead, it highlights the miracle that life emerged here at all. Earth remains a rare world, not because it is perfect, but because it is ours. Understanding superhabitability also inspires scientific curiosity. It encourages us to continue exploring the galaxy, pushing boundaries and questioning assumptions. Every new discovery brings us closer to understanding what makes life possible and what makes some planets more suitable than others. The search for superhabitable worlds becomes a search for our origins, our future, and our cosmic neighbours. It connects us to the universe in a way no other discovery has. The practical implications are equally important. If superhabitable worlds exist, they change the way we think about planetary protection, space exploration, and long-term survival. Humanity is still in its early stages. Our understanding of the universe is just beginning. But discovering better worlds gives us a long-term vision that one day humanity or its descendants might live under more perfect skies, surrounded by ecosystems that surpass Earth's beauty. The philosophical implications are just as transformative. It forces us to ask, if life thrives easily across the galaxy, what does that mean for humanity's responsibility? Are we alone in consciousness, or one among many intelligent species shaped by different worlds? The existence of superhabitable planets increases the likelihood that intelligent life exists elsewhere. It suggests the universe may be teeming with civilizations, each shaped by the unique advantages of their home worlds. The question becomes not whether life exists, but what form it takes. Perhaps the greatest change comes from the realization that habitability is not a fixed quality. It is a spectrum. Earth sits somewhere in the middle. It is habitable, but not optimal. It supports life, but not perfectly. It offers stability, but not the best stability. Superhabitable worlds occupy the peak of this spectrum. They represent nature's finest designs for life-bearing planets. Understanding them teaches us what life can achieve when given ideal conditions. This perspective invites wonder. It expands our imagination. It gives us a universe where life is not confined to a single, fragile world, but scattered across countless planets designed by cosmic forces to nurture life. Earth is one chapter in a much larger story. Superhabitable worlds remind us that the universe is creative, abundant, and full of opportunities for life to flourish. As we continue searching, we may one day confirm the existence of a truly superhabitable planet. We may detect oxygen-rich atmospheres, stable climates, gentle seasons, shallow oceans, and landscapes teeming with potential. If we detect biosignatures, chemical hints of life on such a planet, it will be one of the greatest scientific discoveries in history. It will show us that life prefers worlds better than Earth, and that Earth was never the benchmark, it was simply our beginning. And when that moment comes, everything changes. Humanity will see itself differently. Earth will appear as one home among many. The cosmos will feel alive, welcoming, and full of possibility. Our curiosity will grow. Our desire to explore will deepen. Our understanding of life will expand beyond biology into philosophy, meaning, and identity. Discovering super-habitable worlds is not just a scientific achievement, it is a transformation of perspective. In the end, the search for planets more habitable than Earth is not just about finding new worlds. It's about understanding what life truly needs to thrive, and realizing that the universe may already be filled with places that meet those conditions far better than our own home. Earth gave life a beginning, but it may not represent life's highest potential. Somewhere out there, under softer suns and across calmer oceans, other worlds may already be flourishing. As our telescopes sharpen and our curiosity grows, we step closer to answering one of humanity's oldest questions. Is Earth the exception, or just one of many homes where life can rise? The discoveries ahead may change everything we believe about our place in the cosmos. And as we continue exploring, one thing becomes brighter and clearer than ever. The universe isn't empty, it's waiting.